of children's toys as simple, bright playthings that can maybe teach kids about colors or shapes or imagination. But they've also inspired scientists and engineers for centuries. Humble children's toys have inspired innovations from medical diagnostics to space travel, proving that scientific ideas really can come from anywhere. Consider the button whirligig. It is a classic toy made of a piece of string looped through a button or disc, and it's entertained kids for thousands of years. Hold either end of the string and twirl it like a jump rope, and then when you pull the string taut, the button spins really fast. That's fun, but it also turns out to be very useful because plenty of procedures in medical technology and diagnostics involve spinning a tube really fast. Normally you would do this with a centrifuge. You put the test tube in the machine, set the speed, hit the button, and then wait for a little while. The spinning motion separates the contents of the test tube by their density, with the densest stuff at the bottom and the lightest stuff at the top. For example, let's say you want to check a patient for the presence of malaria parasites. You put a blood sample in a specially prepared test tube and pop it in the centrifuge. It'll come out with yellowish plasma at the top, a layer of white blood cells and platelets in the middle, and red blood cells at the bottom. And the parasites have their own density, so they are in their very own layer. Voila! Now the problem is, all of this equipment can cost hundreds to thousands of dollars, and the communities hit hardest by malaria can't necessarily afford to buy and maintain that equipment. Also, they might not always have the electricity necessary to run it. So engineers and scientists searched for light, cheap, low electricity alternatives. They tried salad spinners and kitchen mixers, but nothing could reach the high speeds of a centrifuge. Then, in 2017, engineers were inspired by a button whirligig. They created a paper whirligig that holds two thin tubes with 20 microliters of liquid, and it spins them at over 20,000 rotations per minute. They demonstrated that this device could work with several types of blood tests, including checking for malaria. And the paperfuge costs just 20 cents each. Now, unfortunately, it didn't hold much. 20 microliters of water weighs about as much as a grain of rice. So, in 2019, a related group created a 3D printed whirligig that can hold 2 milliliters of liquid, spins at 6,000 revolutions per minute, and still costs less than $1 each. Now, you still need a specialized microscope to detect the parasites, but at least this is a start. Speaking of miniaturizing things, remember shrinky dinks? These are made with a sheet of plastic that you can draw on, and then you heat it in an oven, and it shrinks into a smaller version of the original masterpiece. So it sounds like shrinky dinks would be really handy if you're going to try to miniaturize equipment, which is exactly what one group of researchers thought. See, a sheet of shrinky dinks plastic is made of polystyrene. To make that plastic as thin as paper, the individual squiggly plastic molecules are stretched out and lined up next to each other. When the manufacturer cools the sheets, the molecules become locked in place. But polystyrene molecules remember their original state, which is more stable. And when they're heated up again, maybe with some art drawn on top, the molecules return to that disordered state. And like crumpling up a piece of paper, the piece of polystyrene covers less two-dimensional area, but gains height. So inspired by shrinky dinks, researchers from the University of California set out to create better respiration monitors for people with asthma or chronic pulmonary conditions. So right now, hospitals use bulky monitors to measure a person's breathing, ones that don't even provide all of the information doctors want. The researchers wanted to create a convenient device that people can use when they're living their lives outside of the hospital, and that passes on more information about their breathing. It also needed to be small and flexible, so it could be worn under clothes and move along with the user on a walk or run. They created tiny metal sensors that were corrugated like zigzag-shaped cardboard so they could bend without shattering. To do this, they took pieces of polystyrene, put a stencil on top with a large version of their sensor cut out, and sprayed on a coat of metal. Then they removed the stencil, leaving a thin layer of metal in the shape of the sensor on the polystyrene. Next, they heated the polystyrene and it shrunk up like shrinky dinks because it's literally the same material, and as the metal on top shrinks up, it naturally corrugates. Once they had these tiny metal pieces, the engineers released them from the polystyrene and incorporated them into a wearable respiration monitor. One that was much smaller and less intrusive than what we had before, and that provides more important data. Another classic toy is a stack of colorful rings on a wooden post. Its simplicity is truly timeless. But hear me out. What if it was several meters wide and hurtling through the atmosphere at Mach 10 or more? Well, NASA scientists designed inflatable technology that they say was inspired by a child's stacking ring. The problem NASA faced was that when spacecraft land at high speed, friction from the air molecules heat up their surface to sky-high temperatures, like over 1400 degrees Celsius. Vehicles like the Space Shuttle and re-entry capsules beat the heat by entering the atmosphere at just the right angle and by using heat shields. These heat shields work around the Earth because the atmosphere is so dense that it helps slow the spacecraft down. But on planets with thinner atmospheres, NASA needs a different strategy. Meet the Hypersonic Inflatable Aerodynamic Decelerator, or HIAD. Similar to the ring toy, the HIAD is made of a cone-shaped stack of inner tubes. One great thing about using an inflatable heat shield is that only the deflated shape has to fit in the rocket. When NASA tested the HIAD in 2012, it packed down to about half a meter wide, but deployed to 3 meters wide. Eventually, they hope to make HIADs up to 12 meters wide. NASA is planning its next test of HIAD in 2022, when they will be dropping it to Earth from low Earth orbit. If it works, the tool could be used to protect large or non-circular objects as they land, whether on Earth or on distant planets. Or it could also be used to park a spacecraft in orbit around Mars, so NASA can more safely deliver scientific equipment or people to the planet's surface. Last is a technology that scientists actually want to pop, a soft robotics part inspired by jumping rubber poppers. Rubber poppers are those half spheres that you turn inside out and then you can leave them on a surface, and then wait. Just wait, and then pop. In an instant, the inside-out popper pushes itself the right way around. This is called snap-through buckling or shell buckling. The rubber popper is stable before it's turned inside out. When you flip it around, the material on the inside gets stretched out and wants to shrink, and the material that was on the outside is getting compressed and it wants to expand. The sides curl because the material around the edges is starting to return to its more stable state. And once that push and pull takes control of the rubber popper, it flips back in a snap. Because rubber poppers are made of a soft material that can move quickly and with a lot of energy, engineers are using them to develop an actuator for soft robotics. Soft robots are made of material like cloth, water-based gel, or rubber that makes them less dangerous to us soft humans than classic metal robots. Actuators move robots around a bit like our joints. Something like a rod and piston moves robotic parts forward and back, while a motor makes things spin. But pistons and motors are made of metal, and if they're moving quickly, they could really hurt a person. So soft robots need soft actuators. One solution is an inflatable soft jumper. It moves as fast as a rubber popper because it's made with 2 poppers, one nested inside the other. The outer popper is made with thin, flexible material, and the inner popper is made of thicker rubber, more like a popper toy. When the space between the poppers is inflated, the upper, thinner layer expands. But the lower, thicker popper isn't flexible enough to give way for the pressure. When it reaches a tipping point, it snaps inside out, and the device predictably jumps in the air. The engineers who designed it think their actuator could be applied to everything from small medical robots to large scout bots that need to cross complicated terrain. And not just soft bots either, but anywhere a flexible actuator might be useful. All these clever inventions show that you never know where inspiration will strike. So if you're ever having trouble coming up with your next $1 million idea, consider raiding the nearest toy chest. Thanks for watching this episode of SciShow, which was brought to you in part by our amazing patrons. If you'd like to help us make more videos about turning toys into heat shields and everything else cool and curious in the world, you can get started at patreon.com/SciShow.